So today we are going to go through transformer. So what is transformer? Of course, transformer here is not the one that we watch in the movie. It is this thing. This is a transformer. So what is transformed over here is the voltage. The voltage is transformed. Okay, the voltage is increased or decreased. That is what the transformer do. The transformer can increase the voltage or can decrease the voltage. So that is the main function of transformer. So how it works, we just go through the point here one by one. Alternating current can be increased or decreased by using a transformer. So you can increase the current or you can decrease the current. In other words, you can increase the voltage, you can decrease the voltage. Okay, so consists of a primary coil, a secondary coil, and an iron core. This is the three main structure of a transformer. So you can see a primary coil here is the coil on the left. So it is a wire with insulator covering it. So of course you can't expect the wire is connected to the iron core. It's not because there is insulator that cover up the primary coil. So the current is going in and then flow and then come out. And the other thing is we are using alternating current. So the current go in at one moment from here and come out from here. So at the other moment, then the current will go in from here and come out from here. Okay, so it keeps changing directions. That is what happens on the primary coil. So secondary coil is on the right. Okay, secondary coil. What is the function of secondary coil? I will just let you know later. So we have primary coil, secondary coil together with the iron core in between. Okay, now let's see more details. The iron core gets magnetized by the incoming current, and these magnetisms then creates a current in the leaving wire. So this is a very short explanation on what happens on the transformer. So they say the iron core get magnetized. Okay, so I give you more details on this. So first of all, alternating current is connected to primary coil. And that's the thing. So then you should expect the current to keep changing direction. So what happened is the primary coil becomes an electromagnet with changing pole. So when I say changing pole, that means at one moment the upper part become north pole, here becomes south pole. At the other moment, the bottom become north pole, the top becomes south pole. They keep changing pole. So how we determine the north pole and the south pole? Let's see one quick example. Okay, let's say this is your primary coil. Okay, so maybe I put the iron core first. Okay, I will draw it in 2D. So let's see how it changes its pole. Okay, so I coil like this. To make it convenient, I just draw, let's say, just a few rounds. Okay, so they may have maybe thousands round. I just draw 3 rounds only, as you can see. Okay, so like I said, alternating current is where the current keep changing direction. So at this moment, let's say the current enter from here, turn one round, go backwards, and backwards, and then come up. Okay, you want to know where is the North Pole, of course, the best way is, this is a coil. So for coil, we use right hand grip rule. Right hand grip rule. So what to do is you have to turn your finger in this particular way. So your thumb and the forefinger twist in this way. Okay, right hand grip rule. So the four fingers have to twist in a way which follow the turn of the current, the directions of the current. So you see they are going this way. So our finger also turn this way, you see. So turn in the same way with the current. So your thumb point to the north. So meaning that it is north on top here. So here will become North Pole. Here will become South Pole. So the iron core is here, making the magnet to be a stronger magnet, the electromagnet. Okay, so I write it down here. Iron core make the magnet, makes the electromagnet to be stronger. Without iron core, right, the magnetic field which form is a very weak magnetic field. So iron core makes the electromagnet stronger. So it will be something like this. North pole, south pole, the magnetic field is like that. Where North Pole, you can expect the arrow come out from the North Pole. South Pole is going to be like this. Okay, going into the South Pole and coming out from the North Pole. And try to imagine, let's say I extend this line. And then we go all the way back to South Pole. Okay, I purposely extend this line because there is some explanation that I'm going to give here. So when the magnetic field go this way, back to the South Pole, they will reach the secondary coil. They reach the secondary coil. So let's say I draw the secondary coil here. So let's say secondary coil, I just draw two round. So what happened is the magnetic field, okay, write down, the magnetic field from the primary coil cut the secondary coil. Current induced. So that is where it happens here. Secondary coil, I mean the magnetic field come here and the magnetic field is cut by the secondary coil and hence currents produced. So if you want to know in what direction the current is, so you have to use right hand grip rule again. So where in this case, you see the arrow is going down. So if the arrow is going down, that means here is going to be the North Pole. Okay, North Pole. Here is going to be the South Pole. So you make your thumb pointing downwards. So in this particular way, your thumb pointing downwards. And then your forefinger will be like this, like that, and like that. Okay, so where you should expect the current flow in a way that follow the four fingers, which is going to be like this. Okay, so the current will flow in that way. Okay, so that is what happens. So of course, after a while, alternating current in primary coil changes direction. Okay, so poles of the electromagnet changes or swap. That means after a while, the current will flow in this way. So go in from here, turn, and then come out from here. And because of that, here become north, here become south. And the north pole is here, and the direction will come out from here, go out, and go in from here. Everything turns opposite. North-south here. So here will be south-north. Current will change direction. Okay, yeah. Are you trying to say?
So basically, we like extend some part of the wire from the primary coil into the middle of the transformer, so that the secondary coil is induced with current also.
Oh, yes, correct. Secondary coil induced current. That is the main thing. They are not connected, by the way. Okay, so
are they connected by the extended wire from the primary coil?
Extended wire from the primary coil just turn this way and then go away.
Yeah, but you draw a green color like a oval. Yeah, that one.
This is the magnetic field.
Oh, magnetic field from the from the iron coil, is it?
Magnetic field is formed when there is current flowing in the primary coil. So the iron core here will make the magnetic field stronger. So it is not a wire, it is an invisible magnetic field that cut the secondary coil.
So the magnetic field appears because of the magnet.
Because of the current which flow here. The current that flow in the primary coil forms the electromagnet. Try to recall back. This is what we learned. Okay. It's not this. This is the induced EMF. Induced EMF. So here is different. Current flowing in the primary coil make the electromagnets to be formed. So that's the thing. Electromagnets that's formed cut the secondary coil, EMF induced here, and current is flowing in the secondary coil.
Yes, sir. So, because there is a magnet there, so is that why there is magnetic field?
You mean there is a magnet here?
Yeah.
We have to know that this is called electromagnet. Yeah, electromagnet. Electromagnet is there because there is current. Not because we are using magnet. We don't use any magnet, we just use an iron core. We don't put a magnet here, we don't put a magnet. We put a piece of iron here, and the magnetic field is formed because there are current flowing in the coil. The current that flow in the coil forms electromagnets. And electromagnets form magnetic field.
So, which means there is no magnet at all in a transformer.
It is not a permanent magnet. It's a electromagnet.
which is the temporary magnet.
Temporary magnet, yes.
Okay.
When the current is there, then the magnet is there.
Yeah.
When the current is turned off, then no more.
Okay, sir. Understand.
Okay.
So sir, I just have to clarify this.
Uh-huh.
The transformer is basically like a temporary magnet lah.
Yes, temporary magnet.
So when there is current, there is electromagnetism. When there is
Yes.
no current, it is not magnetized.
Yes, correct.
Okay, sir. And
Okay. So that means we have done the third point already. Now let's see the next point. The power is the same on both sides. The both sides that they mean here is the left-hand side, the primary coil here, have the same power with the right-hand side, the secondary coil. Same power. And we have to know that when they say power, right? So we have to know that power equal to VI. Power P equal to voltage times current. So when they say same power, that means the power on the left, which is primary voltage times primary current, or you can call it input voltage times input current, as you can see here. It's same with the power on the right, which is secondary voltage times secondary current. Same. So that's why you can see here. If you don't want to call it secondary voltage and secondary current, you can call it output voltage and output current. So they have the same power. These and these are equal. And so we assume the transformer to be 100% efficient. Then this formula is valid. Okay. Then after that, you can figure out the number of coils and the voltage with this formula. So you have to see, the transformer can increase the voltage or can decrease the voltage. So it is based on the number of turns. Okay? So let's say, for example, if you turn 500 rounds on the primary coil, which is the input coil. Input coil is primary coil, NP. This is output coil. Output coil is secondary. Output coil is the right-hand side, secondary. So, but they use 1 and 2. 1 and 2 or S and P is just fine. Input voltage is VP. Primary voltage, this is VS. So VS over VP equal to NS over NP. Of course, here you will find it to be swapped upside down. They put VP followed by VS. Then here we will just change accordingly. NP over NS. So you can use this. Okay. So how to use the formula? Let's say example. Let's say on the left hand side, I put 500 coin. Let's say example. My primary coin, I turn 500 rounds. My secondary coin, I turn 1,000 rounds. 1,000, I just turn 1,000 rounds. And after that, let's say the input voltage, I just put 5 volt. 5 volt. So I'm looking for output voltage. So in order to find that, we just use this formula. Normally, if I want to find Vs, I will put Vs on top. I use Vs over Vp equal to Ns over Np. And then I substitute Vs over 5, 1,000 over 500. And then I get Vs equal to 5 times 2, which is 10 volt. So that means from 5 volt it become 10 volts. So increase the voltage. That is the main function of transformer, to increase the voltage. Okay, so how to use the second formula? Let's say one example. Okay, now let's say I use 5 volt and my current is 0.2 ampere. So I want to find out my secondary current. I want to find out. Okay, then I can use the formula VPIP equal to VSIS. You can put V1 I1 equal to V2 I2. It's just fine. Primary or 1 or secondary or 2 is just fine. So let's say I substitute with value. So my VP is 5. My IP is 0.2. My VS is 10. My IS is unknown. So here I get 1. Then IS. So IS is hence 0.1 ampere. So I can find out the current, I can find out the current. So you will realize something like this. When you see here double, then you will see here to be half. Like opposite one. If you see here to be triple, then here has to be 1/3. So there is this kind of relationship. If you see this side to be quadruple is like 4 times, then here will be 1/4. So something like that will happen. Okay, so that's how we do the calculations for transformer. Very important. Okay, now let's see more information here. When magnetic field is changed, magnetic field is changed because you are using alternating current. Alternating current keep changing directions, and hence the north pole, south pole will keep changing as well. So when magnetic field is changed, the primary coil, by connecting it with alternating current. So they are trying to say that you want to change the magnetic field, right? You have to connect it with alternating current, not direct current. Direct current, they won't have change in magnetic field because direct current always flow in one direction only. Alternating current, they keep changing in the directions of flow of the current. So that's why magnetic field will keep changing its pole also. So an EMF induces across the secondary coil. So this one I have to explain a little bit. Why we need to use alternating current, cannot use direct current. You try to imagine. When you are using alternating current, like what I mentioned, at one moment, the current flows this way. Then here become North Pole. North Pole is where the magnetic field come out and cut the secondary coil. When they cut the secondary coil, current is induced in this direction. Induced in this direction. After a moment, the current here change direction. Here become North Pole, and here become South Pole. So because of the formations of North Pole here, the magnetic field will come out from here and cut the secondary coil again and induce current again. Then after a moment again, here change direction. Then here become North Pole again. Then the magnetic field will cut for the 3rd time. Then we'll cut again for the 4th time. We'll cut again for the 5th time, and we'll keep cutting the secondary coil and keep inducing current. So that's why we need to use alternating current. If you use direct current, it doesn't work in that way. Direct current, it flow in one direction. Here become North Pole and cut one time and just one time. It will remain as North Pole all the time, if you are using direct current. So it cut the secondary coil for just one time, and the EMF induced is just one time, and after that disappear. Okay, so That's why we need to use alternating current because it keep cutting the secondary coil in different directions and keep inducing EMF. So that's the reason. So now you see some information about iron core. Iron core is this one. The iron core channels the alternating field, the magnetic field, the magnetic field that keep changing its pole through the secondary coil. So that means channel it to the secondary coil. Okay, you can draw like this also. You can draw like this, or you can draw like this. Then inducing and alternating EMF across it. So induce EMF in the secondary coil. Then we have two types of transformer. A step-up transformer increases the voltage. You want to increase the voltage. The idea is put less coin in the primary, put more coin in the secondary. When the number of coil increase, the voltage increase. And this is called step-up transformer. So the idea of step-up is like we make the voltage to go up. Step-down transformer is the other way around. You put more coil here, you put less coil here, the coil decrease. So when the coil decrease, the voltage decrease. That is step down. So the step down here is decreasing the voltage. Okay, now let's see more information about transformer. Transformer used to make high voltage alternating currents.
Sir,
Yes?
for step-up transformer, right, the
Yes.
primary coil will have more turns compared to the secondary coil, right?
Yes, correct.
And then for step-down transformer, the primary coil would be having less turns compared to the secondary coil.
Yes. Can you repeat again for step down? I can't hear clearly. Step down.
For step-down
Yeah.
transformer, the primary coil turns will be lower than the secondary coil turns.
Oh.
The number of
should be the other way around. Primary should be more than secondary. Like going down.
So for
Turns go down.
step up is
Is it step up?
the number of turns in primary coil will be will be less than the number of turns in secondary.
Okay, yes, correct.
Okay.
So where you can see it go up. When it go up, the turns go up, the voltage go up. So that's a direct relation. Okay, so that's the thing.
Yes.
And let's see this part. Transformer used to make high voltage alternating currents. Okay, so that means normally we don't use 5 volt to 10 volt in practice. In practical, we use high voltage. Okay, so for example, I show you one example here. When you want to channel the electricity from the place that you generate hydroelectrics, let's say, to the city. So you can see something like this. Okay, let's say transmissions of electricity and transformer. Let's look at the image only. This should be good enough. So if you look at this picture, from the power plant is the place where they burn the coal or they burn the charcoal to generate electricity, for example, or even hydroelectric will be just fine. Hydroelectric is where the water turns the turbines when it turns, then that will generate electricity. Yeah. So in details, we are not going to care. So what we want to see is the step-up transformer here. Like what I said, you don't expect 5 volt to 10 volts only. So you should expect high voltage, 12,000 volt, step up to 400,000 volt. So high voltage. Power plants is normally at the rural area or in the jungle. So in the jungle, you want to send them to the city. Normally the place that use a lot of electricity is the city. So they have to send it to the city. So they need to step up the voltage so that they minimize the power loss. Minimize the power loss as the current is very small. The current will be very low if you increase like what I said, if you double this, then the current will be half of the original. If you change this by 100 times, you increase this by 100 times, then the current will decrease by 100 times also. That means you have to divide by 100. Okay, so you increase the voltage so much so that the current become very low. When the current is low, power loss is low. So that is the reason why they use high voltage to avoid a lot of power loss. Okay. So then they must use the high pylon to avoid electric shock, maybe from here to here. Let's say you are playing handphone here, maybe you get electric shock easily. Okay, so that's why you have to use high pylon. High voltage, dangerous, so must be far away from the ground, or else the electric will come down. Okay, so when they reach the city area, cannot use high voltage already, dangerous. Many people are walking around. Okay, so they step down to 13,000 volt. Okay, 13,000 volt. Then when they are nearer to housing area, you need to step down some more, 240 volt. Your house cannot take high voltage and dangerous also. So that's where you can see the step up and step down. So that's why the note said we don't use 5 volt to 10 volt one, we use high voltage. High voltage. Okay, so like what I mentioned just now. Next point. Since power loss in a resistor is P equal to I squared times R, having a lower current will decrease the power loss. So you see, these 2 points are interrelated. Okay, so first, in transformer, VP step up transformer will make the VS to increase. VS increases. Let's say VS increases by X times. When VS increases by X time, right, the current will decrease. Current IS decreases. Decreases by how many times? Divide by X times. Here you multiply by X, here you divide by X. So basically the relation is this. So making the IS to be small. Then you put the IS here. The power loss depends on the current. Your IS is now very small. Then the power loss is very small also. the decrease of IS means power loss decrease. So that's the thing in the second point. Now, since transmission cable are many kilometers long, transmission cable, the one from the power plant to the city, the cable, are many kilometers long that have a lot of resistance. So a transformer is used to increase the voltage and decrease the current to decrease power loss. So they give more explanation. We must use high voltage so that current is small, so that power loss is minimized. But high voltage is dangerous, so that's why they have to use high pylon. High pylon. The advantage of high voltage transmission, less power lost. Thinner, light, and cheaper cable can be used since current is reduced. So you can, no need to use copper, no need to use copper cable. Copper cable is very expensive. So maybe you can use aluminum. Aluminum cable is cheaper. So you can save costs as the power loss is minimized already. Okay, so that is all about transformer. Of course, here onwards is something else already. So let's practice transformer first before we do the question here. Okay, transformer, let's take a look. Okay, let's see whether we can do this or not. Related for part A, but let's just focus on transformer first. Okay, so for this is question on page 7. Page 7, so let's see. Figure 8.2 shows a transformer. Then, so you can see the transformer having more turns on the primary coil and less turn in the secondary.
Step down transformer.
Yes, step down transformer. So kind of reasonable because 240 volt is the voltage from our house socket, but our lamp can't take high voltage of 240 volts, so we need to step down. So to make the voltage smaller. The 240 volt main supply is connected to the primary coil P. The voltage across the secondary coil S is 12 volt. Okay, so 12 volt only. So from 240 volt to 12 volt. A lamp in series with a fuse 3.0 ampere fuse is connected to S. So try to recall back the function of fuse. Whenever the current flowing through the fuse is greater than 3.0 ampere, the wire melts and then it will break. The wire break and then the current cut off.
So when the current cut off due to the current received by the fuse is greater, so the phenomenon is called short circuit, right?
Short circuit is actually when the current doesn't reach the electrical device and go back straight away to the source, and then that will be short circuit. Short circuit, they're supposed to go one round and come here. Then, in case where there is some problem, they don't go to the lamp and go back straight. Then that is short circuit.
Okay, understand.
This is different. This fuse, right? This fuse is breakdown. The middle of the wire breakdown because current too big. Then the current can't even flow. Then everything just no current. So current. Okay. Now let's see what else. The number of turns.
So is there any wrong with the network again? Sir, are you there? Sir?
Hello.
Hi, sir.
Can you hear me?
Yeah.
Oh, okay, can. Okay, let's continue. Okay, now let's see here. The number of turns in the coil of the transformer is not shown accurately in figure 8.2. That means you don't go and count how many turns and how many turns here. It's not accurate one. Predict with suitable calculations whether the fuse blows. Blows means the fuse, the wire break, when there is a current of 0.20 ampere in the primary coil. So we have to do calculation. Okay, so let's see how we count it. We just need to count the current in the secondary coil. If it's greater than 3.0 ampere, then it blows. Okay, so we use formula. Vp Ip equal to Vs Is. Just for information, writing out the formula itself will give you 1 mark. I'll give you 1 mark. Okay, then you substitute. We substitute the value. Primary voltage 240, and then current 0.2. Secondary voltage 12 volt. Secondary current, we need to find it. Then secondary current. Okay, so we just count, use calculator. 240 times 0.2, then divide by 12. So we get 4 ampere. 4 ampere is greater than 3.0 ampere. So because of that, the fuse blows, which means melts. The wire melts. So something like that will happen. Okay, and the answer 4 ampere, you get 1 mark. When you say it blow, you get another 1 mark. So altogether 3 marks. So it's a 3 marks question.
So,
yeah.
So basically, what does the 4 ampere refers to?
The 4 ampere is the current in the secondary coil, which means is here. Here is the primary 0.2. And here is 4 ampere in the secondary coil.
Oh, okay.
So the 4 ampere that enter the fuse, this fuse cannot take more than 3 ampere. 4 ampere passing through the fuse, the wire melts.
Okay, sir, I understand.
Okay, so that's the thing. Okay, now let's see another questions. Okay, we just look at transformer only. 3 marks. So no paper 4. We don't expect any marks around this. Sometimes 4 marks or 5 marks maximum. So figure 8.2 shows a direct current supply. You see, they are using direct current. You know, just now I explained must use alternating current. So direct current doesn't work well. They purposely use direct current, and they want you to explain only what will happen. When switch S is first closed, you close the switch. The needle of the galvanometer deflects briefly. Deflect, that means deflect a little bit, then go back to original. Then returns to zero. Return to zero. Galvanometer, right? Make sure you know something like this. I let you look at the actual pictures of a galvanometer. You will get some idea. Okay, let's take a look. Okay, so we look at this. Galvanometer, if you look at the pictures, you understand that the needle is in the middle when you're not using it. You know, when there's no current. When there's no current, the needle should stay in the middle. So after that, it depends on the current. If the current flow to the right, then the needle deflect to the right. If the current flow to the left, then the needle deflect to the left. Okay, so that's the thing that we need to know first. Okay, now let's come back to our questions. That's why the needle is in the middle in the picture here. Okay, so now they say the needle deflects a little bit, then go back to zero. Explain why the brief deflections occurs. Why they just deflect a little bit and go back to zero. So this one I explained just now in the note. Now let's see the answer first. Okay, so first we said there is a change in magnetic field for short time. You know, the current flow, then here become north pole, let's say, then they cut the secondary coil, and it will remain north pole all the time. So the cutting on the secondary coil is just one time. Just one time. So then they will just deflect a little bit, then go back already. Okay, so change in magnetic field for a short time. Or after that, second point, you write changing in magnetic field causes field lines to cut the secondary coil. And then causes induced current. Okay, so 3 points. You just need to explain now what happened. Why there is a deflection in the needle for just a while. Okay, but if you're using alternating current, right, you should expect the galvanometer to deflect to the right, then deflect to the left, then deflect to the right, left, right, left. So showing that it's alternating current. Okay, then let's see another one. It's a very famous question after all. We have a question again and again from transform. Okay, let's see this question.
Regarding the last question about the galvanometer.
Yes.
So basically, a part of it is attached, like the secondary coil, I think, is attached to the
secondary coil attached to
the galvanometer. It is because of like something to do with the Faraday's law thing, right?
Oh, you mean secondary coil did connect to galvanometer?
Yeah.
Not that much related to Faraday law. Faraday law is saying something like if you have a coil and you move the magnet in and out from the coil, the faster you move the magnet, then the greater the EMF induced. That's Faraday law. But this one, we don't move any magnet in and out. It is a magnetic field that cut the secondary coil. It's a different thing.
Okay.
Yeah. So we don't apply Faraday law in transformer.
So, sir, it is said that there's a DC supply in the front of in the transformer. So, what does that mean?
DC supply means direct current supply. Direct current means the current flow in one direction only.
So, just now during the when were discussing about the nodes, you said that for transformers there will be only AC current, right?
Yeah. Transformer
Um,
work well with AC current, not DC current.
sorry, sir.
I
Can
mean
you?
transformer work well when you are using AC current, not DC current.
So, but they can also work with DC current lah, but just that it's not as well. It will not be as well as AC current.
Yes, that's true.
Okay, sir.
Yeah.
Okay, sir. Understand.
Okay. Now let's see another one. These questions. So this is about transformer also. Figure 10.1 shows the charger for a laptop computer. So this is the charger. The charger contains a transformer. Transformer is inside. So the voltage across the primary coil of the transformer is 230 volt. That's the primary voltage. The primary coil has 4995 turns and the secondary coil has 555 turns. Calculate the output voltage of the transformer. Okay, so we just write down the formula. Writing down the formula, you get 1 mark. Okay, since I want to count output, I put output on top. Vs over Vp and S over Np. So Vs unknown. Vp is 230. And S is 555. And P is 4,995. Okay, then I get Vs. Okay, so 555 over 4995 times 230. Okay, then I get 25.6. 25.6. So from here you can see, oh, laptop cannot take high voltage of 230 volt. So that can only take 20 something volt. So that's why a transformer is very important here. State the term used to describe this type of transformer. The transformer that decrease the voltage is called step down transformer. So just like that. Okay, so we have done these questions. And then, yeah.
You knew that it's a step down transformer because the voltage of the secondary is lower than the voltage of the primary coil.
Yes, correct.
Okay, sir.
Yeah. Okay, now I let you try the questions. These questions. Okay, so you have to do the calculation and tell me what you get. Okay, so I wait for your answer.
So can you please give me a few minutes?
Yeah, sure. You try to look at the formula and you see which formula is suitable. Yeah.
The answer is boy.
Okay, yes, correct. Okay, so I believe you have used the correct formula as you get point. Okay, now it's correct.